Alessio Ciccarini from the University of Pisa. The task of our operational unit deals with the developing of a device for monitoring the flow of molecular iodine from the storage tank to the thruster. Molecular iodine in its vapor phase has a distinctive purple color because it absorbs light in the green wavelength range, and our measurement system takes advantage on this optical property. Specifically, at the measurement point, the iodine vapor intersects a green laser beam. The higher the concentration of iodine molecule in the vapor stream, the more the laser beam is attenuated due to the absorption. Dedicated electronics are responsible for continuously recording the laser beam's intensity, and on the basis of the system's fluid dynamic characteristics, it is possible to calculate the iodine flow rate.
I'm a PhD student at the Department of Information Engineering at the University of Pisa. I'm part of the electric propulsion group, and we are developing an aluminum prototype for the mass flow meter in the iFACT project with the use of additive manufacturing techniques, in particular with the use of 3D printing. The method that we are going to use is the fused filament fabrication method, and it consists of heating and extruding a filament with a nozzle to obtain a 3D structure. The filament is made of two parts, a polymer binder and a ceramic powder component. The process is able to construct complex structure that would be very difficult to obtain with a conventional manufacturing process. After the printing phase, we have two processes. The first one is a chemical debinding for removing the polymer binder. The second one is a thermal one, that is the sintering phase, in which we obtain the final material, that is a fully dense aluminum component.
I am Manuel Sarabia, aerospace engineer at the Electric Propulsion Research Group of the University of Pisa, and I am part of the team which is developing the iodine mass flow meter, which is currently being developed in within the iFACT project. This device will allow us to characterize the mass flow rate of the iFACT thruster during the test, and during part of the development of this device requires to test it under high vacuum conditions, which is what we achieved with this facility. It is our facility for developing and testing iodine-fed electric propulsion systems. So this chamber allows us to reproduce the high vacuum environment in which the system has to operate, and we use a diffusive pumping system, which is more adapted for iodine testing, as it is less sensitive to the aggressive nature of iodine. Beyond the typical difficulties of operating these high vacuum systems, which we usually use to develop electric propulsion systems, iodine poses a series of additional difficulties due to its chemical reactive nature, for which we have taken into account during the design of this test facility, such as adding cold surfaces to condensate iodine or chemical traps, also to prevent it to go into the vacuum pumping line.